Okay, for an equation such as dy over dx is equal to x times y, say we have an initial condition, y1 is equal to 5, and we want to find out what the value of y will be whenever x is at 2.6. Now with the so-called exact solution, now in accordance with Maple, you have about 89.071365 and to see how this is going to compare with the four approaches, have Euler at 0.2, 0.05, and it got the Hoyne or improved Euler at 0.2 for the step size, and Runge-Kutta also at 0.2, and just looking at doing a bit of comparing. Okay, so if we work with this equation, and running it through the Euler approach, now you have your equation. Now the initial condition, we have y1 is equal to 5. Now the step size we have at 0.2, and look at it this way. So you're going from x equals 1 to 2.6, so you have a difference of 1.6 units. And if I divide by the step size, this will give you your number of steps. So think of it like 1.6 divided by 0.2. So we have 8 steps, and to see what we have, when looking at what we have for the number of digits, okay. Okay, so we have with the Euler approach, so we have again with this equation, you have the initial condition, so you have y1 is equal to 5, and you're going out to x is equal to 2.6, and again, you're going from x equals 1 to 2.6, so you have a jump of 1.6, and if you divide by the step size of 0.2, this will lead to the number of steps, which will be at 8, and taking what we have to 10 digits, and notice we have 51.009, not exactly close to the exact result, and just looking at the comparisons, and again, just how we have this to be lined up. If you notice, you have Maple's numeric solution and the Euler approach, and notice we have a huge error in this particular regard. Okay, now let's say that if I expand the number of steps, whenever we had step size to be at 0.05, okay, so the step size to be 1/4 the amount, so we have 4 times the number of steps. So you have the number of steps at 32, and for the output, okay, an improvement. Still not exactly close to the mark, and just to see how it lines up. And so you can see here with output equal to information, and just taking what we have and placing it in tabular form. Okay, so I want to go out all the way to what I have for 2.6, so going to tabulate default, and we have at the bottom. Okay, so with the Euler approach, okay, in the step size of 0.2, okay, we have again far from accurate. Okay, see, we have the output at 51.00913 among the first digits, and for what we have for much smaller step size, trying to say that fast 3 times. Okay, so we have much closer, but still quite a bit off the mark, where we have 75.43045.9 among the first digits. Now we're going to move out to the Hoyne method, where the step size is going to be at 0.2. Okay, so again, comparing, when we had the Euler approach with the step size at 0.2, okay, we had a number of steps at 8, and with the step size at 0.05, we had 32 steps. Now we have with the Hoyne approach, what I'm going to do here, okay, is that the opening statement, when I have a Runge-Kutta, Yes, I have the differential equation, y1 is equal to 5, and we're trying to find out what y will be whenever x at 2.6, number of steps is at 8, and for the improved Euler, you have to add in the sub-method equals Hoyne's statement, and we have for the number of digits, we have at 10, and we have for the output, we have substantially closer at 84.232, and just kind of look at the magnitude of the error. And again, just including the output is equal to information. All right. So this is the numeric solution according to Maple. Here's the Runge-Kutta. Still closer. And if I were to go ahead and throw in what we have for what we refer to as the Runge-Kutta method. So if I take, what I have here, and it's almost like the improved Euler statement, except the sub-method as opposed to Hoyne, it will be at RK4. Okay, so I have 89.0283. And so just, again, just looking at how this is going to compare. So again, you have the sub-method at RK4, output is equal to information. And okay, so you got Maple solution, you have the Runge-Kutta solution. So you have the size of the error, just a little bit over 4/100ths. And if I were to take what I have here, and we'll say that for the number of steps, let's say that instead of 8, if I had, let's say, 80 steps. Okay, so you have a very incremental approach. So instead of going up by 2/10ths at a time, I'm actually going up by 2/100ths. And if I look at the final result, and if you notice, you don't have the tabulate command, but we can show all. And guess what? For what we have in the case of Maple's answer, again, we have 89.0713. And then we have with the Runge-Kutta at not 8 steps, but 80 steps. So we have 89.0713. And look at how minimal the size of the error will be. So going back, again, for this differential equation, we have for y at 2.6, and we had the exact result at 89.0713 among the first digits. And as for what we have in the case of the improved Euler, and again, you have right at 84.23249. And as for what we have in the case of the Runge-Kutta approach, again, you have substantially closer at 89.0283.